Hi everyone. What we're going to look at in this video is conditional distributions, both in the discrete case and the continuous case. What you're considering in these sections 6.4 and 6.5 of Ross's textbook is what can you say about a random variable x given that the random variable y equals a certain value? Okay, and you have that x and y have a joint probability mass function if they're discrete, or in the continuous case, let's suppose x and y are jointly continuous, then what are your predictions based on this? And by predictions, we mean what is the probability mass function of x given that y equals a certain value in the discrete case, and can you find the probability density function of the random variable x given that y equals a certain value. It's not just going to be the same as the probability density function of the random variable x by itself. There's going to be a difference. Now you have more information, so if you use that information, then the density in the continuous case and the mass function in the discrete case will be different. Okay? So let's take a look. This is what we're talking about. X and y have joint probability mass function P of x comma y, which as you recall means the probability x equals x and y equals y. What we're interested in, the probability x equals x, given that y equals a certain value. So you know that the outcome of the experiment gave you that y equals a certain value. Okay, well, just recall the conditional conditioning formula, when you have E given F, what does the formula tell you? That the probability of E given F is the probability of E intersect F divided by the probability of F. Okay, so this is the old conditioning formula. Okay. And so you have, that's the probability of x equals x, intersect y equals y, that's this, divided by the probability y equals y. And this, as you know, that's just the joint probability mass function P of x, y. And this is the probability y equals y. And the probability mass function of y evaluated at little y. Probability mass function of y, we'll write P sub y because there's multiple random variables floating around. So when in that case, you should put a subscript. Okay? And you can only define this in the situations where there's no division by zero, so you need that the probability of y equals y is positive. All right? So just using this as motivation, we define the conditional probability mass function of x, given that y equals a value y. We'll write P of x given y like this, and that's a small p, it's not a capital P, of x given y. We write it like this. What does this mean? This is the probability x equals x given that y equals y. Okay, that's this. So from before, you know, we define this just by our knowledge of conditioning, you know, this turns out to be this. Okay, so therefore you define the probability of x given y, where x is x, given y is y, by this formula. Okay, that's what you write for the conditional probability mass function, and it turns out just by the way you want to define it to be this ratio. Okay? And of course, like I said, you need P of y to be positive. Okay. And anyway, just in practice, how do you find this? Well, this is the probability y equals y, where x is anything, y is y. So you just sum up over all the values of x, x comma y. All right. Now, the conditional probability distribution function of x given y. What is the distribution? That is the probability of x less than or equal to x. That's what we had was a distribution, right? The cumulative distribution function. So we define the conditional probability distribution function of x given y is the probability x less than or equal to x given that y equals y, and we write this, okay? And what does that turn out to be? you know, then you just have to take all the values of that capital X can be that are less than or equal to little x and add up all the conditional probability mass functions. Okay, what is this? This is adding up oops. And you're adding it up over all y's. So, I mean, in the end, if you wanted, you could take this out and sum this up and then divide by that, whatever. It doesn't matter how you calculate it. But anyway, this is you adding up the probability. This, if you remember, this is the probability that x equals a given y equals y. So you're adding all these up over all the a's that are less than or equal to x, okay? So this is the conditional probability distribution function of x given that y equals y, all right? And of course, you need to define it for all the y's where the probability of y equaling y is positive. Okay, so these are the two main formulas you have, all right? And I'll just write down what they are. This is the conditional PMF of x given y equals y. And this is the conditional CDF, if you want, or distribution CDF of x given y equals y. Okay? So let's take a look at an example. So the table gives the joint probability mass function P of x comma y of x and y. All right? You need to find the probability y equals 4, the probability x equals 1, and the conditional distribution of x given that y equals 4. All right? And actually, let's one more thing, sorry. The conditional, let's say this case, it's distribution of x given that y equals 4. And in the first case, we look at the conditional probability mass function of x given that y equals 4. Okay? All right, so let's take a look at this. I just threw in the first two just as a reinforcement reminder of how to do this. Okay, so let's take first one. What is the probability y equals 4? Okay, so you know this is the probability that x is anything and y is 4. So what do? Sum up over all the possible values of x of the probability mass function P of x comma 4. Okay, so what are you doing? What you're doing is you're going to this column of 4 and adding up all the possible probabilities. All right, so that will be, I'll just write the whole list. That is, whoops. What can x be? 0, 1, 2, 3, 4. So 0, 4 plus 1, 4 plus 2, 4 plus 3, 4 plus 4, 4. Okay? All right. And just so that you don't get confused, let me color this a different color. Let's put a 4 here like this in blue. Okay, and that's this 4 right here. Okay, so add up all these and what do you have? 0.05 plus 0.04 plus 0 plus 0.01 plus 0.02. So what do you have? You'll have 0.12. That's the probability y equals y. So you can see when you add up values in a certain column, you get the probability y equals that y value that the column stands for. So, I mean, if you want real quick, you can look at probability y equals -1. What are the values for y? -1, 2, 4, 6, 8. Let's write this as a table. It's not asked in the question, but just for you, I'm going to do this. So let's say this. We're looking for the mass function of y. Okay? And so -1, 2, 4, 6, 8. For 4, we already found it. It is 0.12. Okay, what is it for -1? You would add up all the values in the -1 column, so it's 0.35, okay? What is it for 2? You'd add up all the values over here, and it will be 0.09. What is it for 4? We already did, and it's 0.12. What is it for 6? 0.23, 0.28, 0.3. And for the probability y equals 8, we could do it one of two ways. We could do 1 minus the sum of these probabilities, or we could add up the probabilities in this column. Okay, so let's just add these up. 0.1, 0.11, 0.14 is what we get. Okay. And you can check that it is 1. Okay, so what do we have? 0.46, sorry, 44, 0.56, and 0.86, and the sum is 1. All right, and this is just adding up all the probabilities of y equaling y, and of course they need to add up to 1. Okay. All right, that wasn't asked in the question, but just wanted to remind you of this and work it out. All right, let's do part B. In part B, you are asked for the probability x equals 1. Okay, what do? You look at the row where x equals 1, of course, and that is this row. And you add up all the values in that row. Of course, don't add up the 1. All right, sorry. Just add up the probability values in that row. Okay, so what do you have? 0.07, 0.1, 0.15. Okay, so this, if you want, write out the whole thing. Sum over all values of y, p of 1 comma y. So that will be p of 1 comma -1 plus p of 1 comma 2 plus p of 1 comma 4 plus p of 1 comma 6 plus p of 1 comma 8. Okay, adding up all of these values. That is adding up values on that row, just, like we did for y's, we add up the columns, and over here we add up the rows, okay? And what are the values? 1 comma -1, that is 0. The probability of x equaling 1, y equaling 2 is given by that entry. Probability x equals 1, y equals 4 is given by that, and so on. So that is 0.15, and that's the probability x equals x. And you could use the same technique and find the probability mass function of x if it was asked. Okay? And now, what is asked in part 3 is a conditional probability mass function of x given that y equals 4. Okay, so part C, find conditional PMF of x given that y equals 4. Okay, what is this? This is this. That's what you want. All right. Well, what is this? That is this. So this is different for different values of x, and we can create a table for this, okay? So the different values of x, and we will write x given y, x given y equals 4. And this I already asked you in part A, and that is 0.12. Okay? All right, so let's see. What are the values x can be? 0, 1, 2, 3, 4. Maybe we should spread these out a bit. Oops. Okay, well, anyway, we'll just do it one by one. Okay, so this is P of 0, 4 divided by 0.12. What is P of 0, 4? That is 0.05, right? This is 0, 4. Okay, so that is 5/12. 1. This is P of 1, 4 over okay, what is 1, 4? That's the next entry in there, and that is 0.04. I mean, if you want, you can write it as 1/3, but by your work in the past, working with discrete random variables, you know it's oftentimes nice to just leave things with a common denominator. So this will be P of 2, 4. So what are these numbers? 2, 4 is 0, 0.01, and 0.02. So this is 0, this is 1/12, and this is 2/12. Okay? And just a point to note, you remember we looked at the fact that conditioning P of E given F, we saw that that is probability. Over here, you do have the conditional probability mass function. That is a proper mass function, and you must have that these numbers add up to 1, and indeed they do. 5/12 plus 4/12 is 9/12, plus 1/12 is 10/12, plus 2/12 is 1. Okay? So you can check. Sum over x's of in this case it is 4 is 1, and that is true. Okay, so this is the probability mass function of x given that y equals 4. Okay, maybe I'll write given. Okay, and that's the table for that. That's part C. And part D is the conditional distribution of x given that y equals 4. Okay, so what we want is this. Oops, sorry, let me put a 4 there. All right. So what is this? You know that these are the values of x, 0, 1, 2, 3, 4. So if x is less than 0, the probability, this is the probability x less than or equal to little x, given that y is 4, okay? If x is less than 0, you know that is 0. Then what happens? This is just, you know, you can forget that you're doing conditioning and just think of this like you did when you were studying discrete random variables. What happened? At 0, to the left of 0, it's 0, so it stays 0. Then at 0, it jumped to 1/12. Then it stayed at, sorry, not 1/12, 5/12. Then it stayed at 5/12 till 1. And then at 1, what happened? It jumped up another 4/12. It jumped up to 9/12. And it stayed at 9/12 till 2, and at 2, no additional probability was gained. It stayed at 9/12 till 3. Then at 3, it jumped up to by another 1/12, so it jumped up to 10/12, and it's stayed there till 4. Oops, sorry. I should have it, oops, as an open circle there. And then at 4, it jumped up by another 2/12, and it stayed at 1 forever. Okay, so that is 1. Okay, so it's just like you did before. So you're just adding these up, these probabilities. So it is 0 till 0. Then it is 5/12 when you're between 0 and 1. At 1, it jumps up an additional 4/12 to 9/12. And it stays at 9/12 till 3. Then it jumps up an additional 1/12. And it stays at that till 4. And then at 4, it jumps up an additional 2/12. And for all x is bigger than 4, the probability x less than or equal to x, given that y is 4, is 1. So this is part D. This is the conditional CDF of x given that y equals 4. Okay? Now, nobody could have asked you this kind of a question where you were asked, given that y equals 5, because y is never 5. So you cannot condition on something that has probability 0 or that never occurs. Okay? So that's what you have in the discrete case, not very hard. You're using a lot of the techniques that you had when you just studied discrete random variables. All right.